Okay, so on to extremal graph theory proper, or the very beginnings of extremal graph theory. We're concerned with forcing a desired subgraph by assuming that we have a lot of edges on a given number of vertices. Okay, so every extremal graph on some number of vertices without containing h is clearly edge maximal without containing h. If you add another edge to this particular graph on n vertices, you will create a copy of h as a subgraph. But it's not clear that all these edge maximal graphs without an h subgraph have the same number of vertices. There might be different ways of getting edge maximal, right? And that's why I made such a fuss about maximally planar graph all having the same number of edges, for example. Or in the last lecture, the graphs not having a K4 minor all having the same number of edges. And I said that's very surprising and not at all clear and so on, and maybe you didn't find it surprising. I'll tell you why it's surprising now. So for example, when h is the path of length 3 with 3 edges, then here are 2 edge maximal graphs on 4 vertices. So both these are edge maximal without containing a path of length 3, right? If you add any further edge to this graph, it has to join those two K2s, and you'll have a path of length 3. And similarly here, you don't have a path of length 3 just yet, but of course, if you add another edge, you do get a path of length 3. And they don't have the same number of edges. They're both edge maximal. But at most, one of them is extremal. That one certainly is not extremal. Okay, right. So let's ask or start with H being a complete graph, say a KR. And let's ask how many edges will force a KR on n vertices. So here's a start. If we have a complete bipartite graph, so that's complete multipartite graph. So we have some vertex classes, and inside a vertex class, we don't have an edge, any edges. Right, no edges inside a class, but all edges between different classes. Then if we have fewer than R classes, then we don't contain a KR. Right, because we can't have more than one vertex from each class, and if there are fewer than R classes, then we can't have a KR, but we have a pretty high number of edges. Okay, so suppose we have exactly R minus 1 classes. Then do they all have the same number of edges? Or is there a way of choosing the sizes of these classes? There's nothing else we can choose once we're assuming that we have R minus 1 classes and are complete multipartite. So if we choose the sizes of these graphs and of these classes in any particular way, can we maximize these edges compared with other ways of choosing those sizes? Yes, we can. So it turns out, and it's easy to see, that we maximize the number of edges in such graphs if the vertex classes have sizes as equal as possible. Right? It may not be possible due to divisibility, then if R-1 doesn't divide n, then we can't have them all the same size, but if we have them as equal, these sizes as equal as possible, so they differ by at most 1, then that maximizes the number of edges. And the reason is that if we had a class with 2 vertices more than some other class, we could just move one of those vertices from this class to that class, and then thereby increasing the number of edges without changing the assumptions that we have a complete multipartite graph with this given number of classes. And why does that increase the number of edges? Well, when this vertex is here, it sends edges to all these. And while it's here, it only sends edges to those. And if these are 2 less than those, then that number of edges will go up when we move that vertex. So the sized as equally as possible. Right? Equal classes of sizes as equal as possible. And then there's a unique such graph up to isomorphism. Right? And how many classes are one bigger and how many are one smaller would just follow from the number n of all vertices that we have. So then there's a unique such graph, and it's called T, upper index r minus 1 of n. N is the number of vertices we're assuming. Right, why is it called T? Because it's named after Turán. Turán proved the theorem that describes precisely the extremal graphs for h equals kr. We're going to do that in a moment. And what we have to show now is that, or what we will show, let me just (1941). He was a Hungarian mathematician, and he was working at this notorious time on some railway problems, and I don't know whether this theorem had anything to do with it or whether he just did it on the side. Anyway, so he proved the following, that for every n, for every g, if G doesn't contain a KR and has the largest number of edges, and the number of edges is this extremal number, then G is this one particular graph. In particular, its number of edges is whatever that number of edges is. All right? And what is that number of edges? Well, let's work it out just quickly. So the number of edges here it's denoted similarly to this as TR minus 1 of n. And what's that? Well, every vertex sends edges to all the vertices in other classes. How big is a class? Let's assume, just for once, that R minus 1 does divide n. Right, then this has such a class, has size n over R minus 1. Right? And every vertex sends edges to all the other classes. How many other classes are there? Well, R minus 2 other classes. So it sends edges to R minus 2 times whatever those class sizes are, this. So let me write that in yellow to make it a little more visible. So it sends edges to R minus 2 times n over R minus 1. And I write that like this, R minus 1 times n, right? That's the degree of every single vertex on the assumption that R minus 1 divides n. Okay, there are n vertices, so we have this times n. That gives us an n squared here, but we're counting every edge twice now, so that gives us a half here. And that is the exact number of edges when R minus 1 divides n. And if it doesn't, well, it's just a little bit smaller. And that's a similar argument to what we had earlier. Well, no, you have to really look at degrees and show that the maximum is attained by when all classes are equally sized. Okay, so that's roughly the number of edges that we can have in a Turán graph. These are called Turán graphs. And the theorem now is that as soon as we know that our graph G doesn't contain a KR as a subgraph and has this number of edges, not necessarily exactly this, but whatever the maximum value is, then it is in fact this particular graph. Okay, questions about the statement, about the definitions? No? Okay. Let's do induction on n. If n is less than r, then we're done as long as we define partitions correctly. So we, for once now, not otherwise in this course, but for once we allow empty partition classes. So if you have at most R minus 1 or even fewer partition classes, then the extremal graph is clearly a Kn, right? It doesn't contain a Kr because it doesn't have enough vertices, but it has all the edges you can possibly have on its number of vertices, n. So we want a Kn to be the Turán graph when n is less than r, and that allowing empty partition classes will allow that even when we insist on having R minus 1 classes. Okay. Now, let n be at least R. Right, so by induction, no, not by induction, clearly, our graph with the maximum possible number of edges contains a kr minus 1. Right, if it didn't, we could add any edge, and we can't be complete now, so we could add any edge and still would not create a kr if it didn't already contain a kr minus 1. So it does, and let's call that k. Okay. Let's give its vertices names, x1, x2, all the way to x r minus 1. Okay. For every I from 1 to r minus 1, for every I let vi be the set of vertices outside this k that are not adjacent to xi. Okay, so we have, I don't know, all the vertices not adjacent to x1, all the vertices not adjacent to x2, and so on. I drew this slightly provocatively. That's not going to occur, but we don't know that yet. So these will turn out to be disjoint, but we don't know that yet. That's just a definition for now. We do know that every vertex in the rest sends an edge to, a non-edge to at least one xi, because if it was adjacent to all the vertices in this kr minus 1, we'd have a kr, and we don't have a kr. Right, so these vi, these sets, these classes vi, they certainly cover all the other vertices. Okay. So then, observe two things, which I'll call 1 and 2, and I'll write up here. So 1.
In the definition of the VI, it shouldn't be G and not G minus K. Because
Sorry, here?
yeah.
All the vertices in G minus K?
No, it's all the vertices in G, at least that's what it says in the book, and else the xi wouldn't be in.
Yeah, you could include the xi's themselves in vi. Okay. Yes. Okay, if the text says that, then I can do that. That's fine. Let me just check whether my version says that too. Yes, it does. Okay. Okay, fair enough then. It won't make a difference. I'll be talking about these vertices outside K as well, but never mind. So observation 1 is that in the rest of G, we know that we don't have a KR subgraph, right? So the number of edges in G minus K is at most however many edges you can have on its number of vertices. And what's its number of vertices? N minus the vertices in K. So N minus R plus 1 if you don't want a KR. Right? You can't have more than this number of edges, because if you did, you'd have a KR just outside K. And the second observation is that every V in G minus K, but now really G minus K, sends or is adjacent to at most R minus 2 vertices in K. Right? As I said earlier, it can't be adjacent to all of them, or else we'd have a KR already. Okay, that's property 2. And now we'll do something really weird. Consider a graph which I want to call G prime, and that's defined as follows. A Turán graph on V of G minus K. So out here, we'll take a Turán graph, one that realizes this number of edges. Classes, well, let's call them Vi prime. No, there are no vertices of here involved. Joined completely to K minus xi for all I. Okay, so we have a Turán graph on here. And we know a Turán graph on whatever number of vertices, if it's a Turán graph with respect to KR, comes in R minus 1 classes. We're calling these classes Vi prime. And the ith class gets joined completely to K except to xi. Okay. Now, this doesn't contain a KR. Well, it's easy. Forget this picture here. I'm talking about the imaginary picture of my Vi primes here. If we had a KR, or any complete graph in G prime, let's phrase it like that. Any complete graph in G prime has at most one vertex in each class, because the classes are independent sets of vertices. Right? It has at most one vertex in each Vi prime, let's call it little vi. And then it might have some vertices in K, but what vertices? If we have a little vi in such a class, in our complete subgraph of G prime, then the corresponding xi cannot be in that complete subgraph because the little vi doesn't send an edge to xi. Right? So the i's for which xi is in our imaginary complete subgraph of G prime are i's that are not among those i's for which we chose a little vi from big vi prime. So all these indices I, either for a little vi or for a little xi, all these indices I are in the set from 1 to r minus 1. And for every little I, there's at most one vertex, either a little vi or an xi. So our complete graph of G prime has at most r minus 1 vertices. Okay, so we don't have a KR subgraph, but G prime does satisfy 1 and 2 with equality, and hence, so does G. And this is where we need this, right? G prime is one particular example of a graph on n vertices that doesn't have a KR. G prime. G is one that has the greatest number of edges that's possible without having a KR by definition. So G has at least as many edges as G prime. But G and G prime agree on all the pairs of vertices that don't contribute to 1 or 2. Those are the pairs of vertices in K. And G prime agree on those, they're always edges. Right? The only possible pairs of vertices where G and G prime might not agree are pairs where one vertex is in K and the other is not, or pairs outside K. And both these are governed by 1 and 2. So since G prime satisfies these two with equality by definition of G prime, G cannot afford not to do that. It also has to satisfy both these with equality because it has at least as many edges as G prime does by definition, like this and that. Okay. But now, since G satisfies 2 with equality, we know that the VI are independent sets of vertices. If we had an edge between 2 vertices in VI, and each of them, by equality here, sends r minus 2 edges down here, well, not to little xi, so to all the others by equality here, then these two with all the others would create a KR. We don't have a KR. So there can't be an edge there. So I'll continue here. And therefore, G itself is a Turán graph, which we wanted to show. Why is that? Well, we have seen that G satisfies 1 with equality, and therefore, by the induction hypothesis, K is non-empty, so G minus K is smaller than G by the induction hypothesis, since it satisfies this with equality, it has the largest possible number of edges without a KR, it must be a Turán graph. So G minus K is a Turán graph. And G minus K is also covered by the sets VI, the original sets VI, that are all independent because of equality in 2, as we just saw. So if we have a Turán graph that's covered by R minus 1 independent sets, then what can these sets be? They must be the classes of the Turán graph, right? Because everywhere else are edges. So if we have R minus 1 set of independent vertices whose union is the entire set of vertices of a Turán graph, then those classes of vertices will have to be the original classes of the Turán graph. So in particular, all these sets Vi minus little xi have the same size up to 1, they're as equally sized as possible. And so the original Vi, including the sets xi, are also as equally sized as possible. And so that implies that G itself is a Turán graph as well as claimed. Second proof of Turán's theorem. We'll use something called vertex duplication. When we have a vertex V adjacent to some other vertices in some graph, right, then duplicating that vertex means adding a new vertex, V prime, and making it adjacent to exactly the neighbors of little v, but not to v itself. Okay? That's vertex duplication. And now here's a very, very short proof of Turán's theorem. We have our G that has the largest possible number of edges without containing a KR on its number n of vertices. And by this argument, it's enough to show that G is complete multipartite. And then we know that the number of classes is as large as it can be, namely R minus 1. Can't be R, because then it would have a KR, right? Then it has the largest possible number of classes, and they have sizes as equal as possible. So from earlier, it suffices to show that G is complete multipartite. Suppose not, then what does your memory say? Third time we have this. Stupid reformulation of not being complete multipartite. Then non-adjacency is not an equivalence relation. Right? In a complete multipartite graph, non-adjacency is an equivalence relation because you have these equivalence classes. Okay, if G is not complete multipartite, then non-adjacency is not an equivalence relation. So there exist x, y1, y2 such that x is not adjacent to either y1 or y2, but y1 and y2 are adjacent. So that's a violation of transitivity, right? This is related to x by the relation of being non-adjacent. This is related to that, but this is not related to that, okay? Non-adjacency is not an equivalence relation, so the only way it can fail is by not being transitive, and that's this situation here, that it's not transitive. Right, and then it's easy. If the degree of x is at most, no, I think I want bigger. Smaller. If the degree of x is smaller than the degree of y1, say, then, well, since they're not adjacent, we can delete x and duplicate y1 to have more edges on the same number of vertices without creating a KR subgraph. That's something I ought to have said here. Vertex duplication can never create a KR when there wasn't one before, right? Because these two vertices are not adjacent. So if that is in a KR, then this is not, but then we can replace in that KR this vertex with that vertex, and we had one before. Okay, so vertex duplication does not create a KR when there wasn't one. So we can now delete x and then duplicate y without creating a KR, but we will increase the number of vertices because this was the number of edges, because this sent edges to fewer vertices than y1 did. And when we duplicate y1, we really get its degree back. We get its degree another time. The fact that we deleted x earlier doesn't reduce the number of new edges because there's no edge here. Okay, so if the degree of x is less than the degree of yi, deleting x and duplicate this y, and that will give you a contradiction to the assumption that G has the extremal number of edges on n vertices without a KR. Okay, so other case. This is not the case. So d of x is at least d of y1 and also at least d of y2. Right? It's not smaller than either of those two. Now, delete both y1 and y2 and duplicate x twice. Right, so what does that give us? How many new edges do we get? We get degree of x twice. Right, because when we have deleted y1 and y2, and we duplicate x twice, every time we duplicate x, we get degree of x edges in addition, because y1 and y2 weren't recipients of edges from x. Okay, so we do get we gain 2 dx edges, and we lose how many edges? Well, degree of y and degree of y1 and degree of y2, degree of y1 and degree of y2, but when I write a plus here, I'm counting this edge twice. So the number of edges we lose is actually smaller than this sum. So that is strictly smaller than 2 d of x. And we have a contradiction, right? End of proof. Yeah, so, I mean, maybe it comes from this proof. Maybe the idea comes from that proof. So these little vi's up there are something like clones of the xi's. But I don't know. Yeah, so the population of graph theorists is divided over how aesthetic such proofs are. And most people say, oh, wow, isn't that great? Such a neat little argument, and it's exciting, and it's so elegant and so wonderful. And yeah, and I can't quite follow them because I don't know what's going on. So it seems like a little bit of magic, and yeah, and then you have it, and you're no wiser than before. Yeah, I feel I am a little wiser than before because we analyze structure that we know must occur in an extremal graph. We know there must be a complete graph, kr minus 1, and then there are all these other edges and vertices, and you can't have another vertex adjacent to everything, so every vertex has a non-neighbor, and we sort of work exploiting what we know, and then we see more and more structure, and then there's this clever bit of comparing the structure that we see with the hypothetical structure that we would have if we had an extremal graph outside K. So yeah, there is a bit of ingenuity there as well, but I sort of like that much better than this. I mean, there's certainly a lot of skill in coming up with such proofs, even if they're just extracted from that, which I suspect might have been the case. So anyway, questions? No. Okay. On to the Erdös-Stone Theorem. You know Erdös by now, Paul Erdös. And the stone in Erdös-Stone is R.Diestel. He was a topologist. And the anecdote that I heard of how the Erdös-Stone Theorem was born was that R.Diestel was giving a talk about his research, and Erdös was sitting in the front row as he used to, and sleeping as he used to. He used to say, well, I can concentrate best with my eyes closed, which is a line I'm always tempted to borrow, except it would be not seem right to borrow anything that's Paul Erdős is famous for having said. So he was there ostensibly sleeping, maybe not sleeping, and then the talk finished. Questions, no questions, and then Erdős had a question, one question. And this one question led to the Erdös-Stone Theorem, which I'm going to show you now, apparently. So maybe his subconscious was listening, or some part of him was. Right, so this Arthur Stone, by the way, was one of a gang of 4 undergraduates at Trinity College in Cambridge. The other 2 were Brooks, as in Brooks's theorem, somebody called Smith. There's also Smith's theorem, but we're not going to touch that, and Tutt. So those 4, they also have a pseudonym together, Blanche Descartes. Their first initials somehow form something like Blanche together, and then, of course, Carte Blanche is the... Anyway, so there are some theorems, some papers, and some not-so-serious stuff published by Blanche Descartes. Tutt used to use that pseudonym for a long time. Some of these are substantial things. Okay, now let me start in a provocative way. Turán says that T r minus 1 of n plus a little bit epsilon edges force a KR subgraph. Right? That's the largest number of edges you can possibly have on invertices without having a KR subgraph. And if you have a little more, of course you have to have at least one more, but let me write epsilon. Then you do get a KR subgraph. Now here comes Erdös-Stone. If you have the Turán number plus epsilon n squared edges, and that isn't very much, because we're in the region of sort of the order of n squared edges anyway with this, right? So r minus 2 over r minus 1 is something like 9/10, right? So that's pretty close to the number of edges you can possibly have on n vertices n choose 2, right? And the Erdös-Stone theorem says if you just have epsilon times n choose 2, or 2 epsilon times n choose 2 edges more, which is not very much because you can choose the epsilon, then you get not just a KR subgraph, but a KRS, a complete multipartite graph with R classes and S, size of partition classes, as big as you like. Okay, so for every R, and every S, as big as you like, and every epsilon as small as you like. If you have this many edges, you get even a KRS subgraph let me just write informally, for n large enough. Right, so for all R and S and epsilon, there exists an n naught such that all graphs like that if n is bigger than n naught, satisfies that. Right, so KRS is a big graph teeming with KRs, lots and lots and lots of KRs. Choose any vertex from each of these R classes, and they make a KR, lots of KRs. Right, so just a few more edges give you lots of KRs, not just one. Okay, so that's the Erdös-Stone Theorem, which is sort of looks substantial, but it's, well, it's an extremal theorem about one particular graph. And you might ask, well, why should we be interested in this one particular graph? So let me tell you why you should be interested in this one particular graph. We can ask more generally, what is the extremal number for H, for any graph H? Right, we just treated KR. This theorem treats KRS. We're not going to prove the Erdös-Stone theorem. That's proved in graph theory 2 using the regularity lemma. One doesn't have to use it, but it's a very nice exercise in applying the regularity lemma. So that's reserved for graph theory 2. But those are the only H's for which we, assuming this, now know the extremal number of edges without containing that. Now, when H is KR, then H, let me divide it by n choose 2, just to make the numbers a little easier to compare. That goes to R minus 2 over R minus 1 when n goes to infinity. Right? R minus 2 over R minus 1. We have this as an upper bound, but we get very close to the upper bound. And in the limit, when n goes to infinity, that doesn't matter. And also the difference between half n squared and n choose 2 disappears in the limit. Right? So we know about the extremal number for NH in the case of H equals KR, exactly what this extremal number is when we divide it by the number of possible edges on n vertices. So what about H equals KR? Sorry, KRS. Using the Erdös-Stone theorem. Well, it's smaller than this divided by n choose 2 for every epsilon. You can choose the epsilon and the limit will be below that. So it's the same. Now here's a lovely corollary. That's due to Simonovits, Mickey Simonovits. Much later than the Erdös-Stone Theorem. So Erdös-Stone Theorem was 41 or something, 46, and this is more like 64, who noticed the following corollary, which has a one-line proof, but which answers this question. And that is, that for every graph H, asymptotically, the extremal number of edges on n vertices forcing H that you need, divided by the number of possible edges, goes to a limit which, for these two particular choices of H, we know to be r minus 2 divided by r minus 1. Now, what could that number be for H, for any H? I won't have you guess, because you can't guess. It's completely ridiculous. It's the chromatic number minus 2 over the chromatic number minus 1 of all things. Right, this mysterious invariant that we don't understand, now suddenly it comes up here in defining the limit for the extremal number of edges forcing an arbitrary graph H. It's determined by its chromatic number. And that has a one-line proof from this theorem, from the Erdös-Stone Theorem, that ostensibly is only about one particular graph. Okay, so let me prove that corollary. We have the Turán number of n is at most the extremal number. No, I should start differently. Let R be the chromatic number of H, and let S be large enough. So, for example, the order of H. We want to apply Erdös-Stone, so we need an R and an S, and these are the R and the S that we take. Right, then the Turán number for n is at most x of nh. Why is that? R is the chromatic number of H. So H cannot be a subgraph of the Turán graph. If it was, it could be colored with the classes, color classes from that Turán graph that hosts it, which is R minus 1 colors only. So if H needs R colors, then H is not a subgraph of the Turán graph. So the Turán graph is a candidate for this. This is the largest number of edges you can have without an H subgraph. The Turán graph doesn't have an H subgraph, so its number of edges is no bigger than that. That's what this says. Okay, and this is at most, I don't want to write that. I don't have notation for that. So let me just write the extremal number of n and KRS. Right, why is that? That's because H is a subgraph of KRS. H has chromatic number R. Color it with R colors. And the classes here, due to our choice of S, are big enough to absorb these color classes. So we can embed H in KRS. So H is a subgraph of this. So if a graph doesn't contain KRS, as these extremal graphs don't, then it certainly won't contain, sorry? No, if it doesn't, sorry. The graphs that don't contain H cannot contain this, because then they would contain H, because H is in here. Right? So the graphs that don't contain H, and those here, those that realize that, are among those graphs that don't contain H. They have the largest number of edges for those, but still they don't contain H. And the graphs that don't contain H cannot contain KRS, because H is in there. So these graphs that don't contain H have at most as many edges as you can possibly have without a KRS. Okay. But now, yeah. This is at most Trn plus epsilon n squared by Erdös-Stone. Right? Yeah. Now take this inequalities, these inequalities, divide the whole thing by inches 2. Then these will tend to limits which are as close together as you want them by choosing epsilon small. So we've got to have equality in the middle after dividing by n choose 2 for in the limit. Okay, so that proves that this extremal number, which we were after, is in fact this, after dividing by n choose 2, with R meaning chromatic number of H. This. Isn't that brilliant? Okay, questions?